Hello, myself Dr. B.J.D. Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about logic micro operations. At the end of this video, the student would be able to understand what are various list of logic micro operations, how they can be applied, and what is the hardware requirement for these logical operations can be clearly understood. The agenda of this video is what are the various logic micro operations, what is the hardware requirement to implement these logic micro operations, what are variety of selective logic micro operations, what are shift operations, and the hardware requirement for implementation of shift operations. So what are the logic micro operations? In the last video, we discussed about the arithmetic micro operations. So the micro operations are majorly categorized into three types: arithmetic micro operation, logic micro operation, and shift micro operation. So here, the arithmetic operations can be applied on the entire content of the register. So the examples of various arithmetic micro operations are add, sub, mul, sub, sub, div. All these are the various mnemonics that can be applied in the assembly language to implement these arithmetic micro operations. And what are the circuitry behind it, we discussed in the last video. Now coming to this video, we will discuss about the two categories of micro operations, the logic micro operations as well as the shift micro operations. The logic micro operations are specify binary operations for string of bits stored in the registers. So these logic operations has to be applied on the part of the each bit of the register also. These operations can be considered each bit of the register separately and treat them as binary variables. So here these logic micro operations has to be applied on each bit of the register. And there are 16 different logic micro operations. And the special symbols that can be used for these logic micro operations can be to represent AND operation, the inverted caret symbol, to represent the OR operation, the inverted caret symbol, and exclusive OR operation can be represented by plus surrounded by the circle, if then has to be represented with a arrow. So the basic logic gate operations like AND, OR, NOT, exclusive OR has to be generally performed by using these logic micro operations. To represent the AND logic micro operation, the caret symbol can be used. OR micro operation, inverted character can be used. Exclusive OR can be represented with a plus surrounded by the circle, if then can be represented with an arrow. Now we'll see, there are 16 logic micro operations. So what are these logic micro operations? The first operation, logic micro operation, is clear. So here the clear operation can store 0 in all bits of the register. So here F has to be loaded with a 0. This is the RTL notation that can be used to represent the clear logic micro operation. So 0 has to be loaded into the F. The second operation is if you take two registers X, Y, the AND operation can be applied. The AND generally performs the multiplication operation. The logical AND can be represented with this caret symbol. So here A, B are the two registers. In between, the logical AND can be applied and the result has to be stored in the F. This is the RTL notation of AND logical micro operation. Next, the third logical micro operation is the first variable can be taken as it easily and can be ended with complement of second number. So here, which has to be represented, the second number can be complemented. So here complement of B can be ended with the first register A and the result can be moved or transferred to the F. So this is the third logic micro operation that can be represented. Next is the fourth micro operation. The next micro operation is simply moving or assigning the value of first number into the F. So here register A content can be moved or transferred to the F. So this is the next logic micro operation. Next operation is the first number is complemented and can be ended with the second number. The first number complement can be ended with the second number. So here A register is complemented and can be ended with the B and the result can be transferred to the F. So this is the representation of this X complement Y. Next logic micro operation is simply moving the second number to the register. So here we are assigning the Y value to the F. So here Y value has to be stored in the B register. B value can be transferred to the F. So this is the representation of this Y value assignment to the register. Next logic micro operation is X exclusive OR Y. So the exclusive OR operation can be applied between the two numbers. How? In the RTL form, this micro operation can be represented is A register exclusive OR symbol can be plus surrounded by circle and the B value. So here two numbers can be, the exclusive OR operation can be applied between the two registers A and B. The result can be stored in the F. Next logic operation are X plus Y. Plus operation can be generally performed with the OR logic micro operation. So here the RTL representation of this X plus Y is A, and to represent the R we are using the symbol inverted character. So A inverted character B. So R operation, logical R operation can be applied on A register as well as B register. The result can be moved to the F. So this is the representation of logical R operation. Next operation is X plus Y whole complement. So R operation can be applied on the register and whole complement has to be taken. So here the RTL notation of this logic operation is the first register A, R operation of B and whole complement. Here the complement can be applied and the result has to be moved to the F. So this is the next logical operation, representation of next logical operation. Next, the ninth logical operation is X exclusive or Y whole complement. So logical exclusive OR operation can be performed between the two registers and the whole complement can be taken. So here X value can be moved to the A register Y value can be moved to the B register. Exclusive OR operation can be performed between A register and B register, and to represent the whole complement, here the complement operation can be applied. So the result can be transmitted to F. So this is the RTL representation of exclusive OR operation whole complement. Next logical operation is the Y complement. So the second number can be moved, the complement of second number can be moved to the F. So the second number can be stored in the B register, and the complement of this B register can be moved to the F. Next logical operation is X plus Y complement. To perform the plus operation, or logical operation can be applied, and the second number complement can be odd with the first number. So to represent in RTL form, the second number Y can be stored in the B register, and complement can be applied, and the OR operation can be applied with the first number. The result can be moved to the F. Next logical operation is X complement. The first number can be complemented, and the result can be stored in the F. So here A value is complemented, and the result has to be moved to F. Next logical operation is X complement plus Y. The first number can be complemented. To represent the plus operation, we have to use the OR logical operation here, and the complement of first register can be odd with the second register B. The result can be stored or moved to the F. So this is the RTL representation of this micro operation. Next logical micro operation is XY whole complement. So here multiplication. So here the multiplication can be represented with AND symbol, and complement can be the NAND operation. So here the first register is ANDed with the B register, and the whole complement and complement can be NAND operation, and in the RTL form it can be represented like this. Next one is moving a 1 value to the F. So all bits of the register can have a 1 value and can be represented in the RTL like this. So all these are the 16 logic micro operations that can be applied. And here is the truth table of these 16 micro operations. So just now we discussed how these operations can be logic or in the RTL form, how we have to represent all these operations. And we have to apply the truth table for these functions. X and Y are the two variables. For the two variables, we are having 4 binary possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. The first F0 is loading all zeros to the F. So F0 is all zeros has to be loaded here. Next, in the F1, X into Y operation can be performed. XY is 0, 0. After multiplying, F1 is 0, and next combination of XY is 0, 1. So here multiplication 0, 1, 0, multiplication 0, 1, 1. Then the value can be 1. And F2 is the next logical micro operation. What is F2 logical micro operation? XY complement. The second number can be complemented and can be multiplied with X. In case of 0, 0, it can be 0, and 0, 1 can be 0, and in case of XY, Y complement, it can be 1. 1 into 1, 1. And in case of 1, 1, it is 0. So this is the truth table of the F2 micro operation XY complement. And in case of F3, the X value has to be moved. So here the X value as it is moved here in the F3 value. Next is F4. X complement multiplied with Y. So here in the F4, when case of x, y 0, it can be 0. In case of 0, 1, x value can be complemented 1. 1 into 1, 1. And 1, 0, 0. And here also, it can be the 0. So this is the F4 operation. So like this, the truth table has to be performed on the 16 logical micro operations, whatever we discussed, by taking the input to the x and y with 4 possible binary combinations 0, 0, 0, 1, 1, 0, 1, 1. So this is the truth table of 16 logic micro operations. How these logical operations can be implemented with the electronic circuitry, we will discuss with this diagram. Here we consider 4 logic micro operations with the 4 logic gates. The gates that can be considered are AND gate, OR gate, exclusive OR gate, and also the complement or the NOT gate. And these 4 gates can be given two inputs A and B. The bits of A and B, successive bits of A and B can be supplied as input to this circuit. And here 4 logic micro operations. In order to select these gates, 2 control inputs can be required. Those selection lines can be S0 and S1. Those can be given as a 4x1 multiplexer. So the output has to be taken as EI. So this is the representation of one stage of logic circuit. So here when the S0, S1 values with the 2 selection lines, the binary possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. When selection lines, both the selection lines are 0, the AND gate can be activated, the input A and B can be ANDed, the output has to be represented in the E. So E is equal to A and B. In case of the selection lines 0 and 1, OR gate can be selected and the input of A and B can be ORed and the output E can be represented this OR operation. Next, when case of 1, 0, the selection lines, the exclusive OR gate can be activated and the input A and B exclusive OR can be applied and can be represented the output in the E. Next, in the fourth combination, when S0 and S1 is 1, 1, then the complement operation or the NOT gate can be activated and represented the output in the E. In this way, the logical micro operations can be represented. So, this is the one stage of logic circuit which can be performed for logic micro operations. Apart from these 16 micro operations, additionally we can have some selective logic micro operations. These selective logic micro operations are includes selective set operation, selective complement, selective clear, mask operation, insert operation, clear operation. All these are various selective logic micro operations. We will discuss one after another these selective logic micro operations. The first operation is the selective set operation. Selective set operation sets one the bits in the A where there are corresponding ones in the B. 2 registers are to be considered, A register and B register. In the B register, where there is a representation of one bit, the corresponding bit of A register can be changed into 1. So that operation is called selective set. Selective means in the second register when there is a 1. Set means the corresponding bit in the another register has to be setted as 1. So here consider one example. So here A is the register which contains the value 1010. So this is the initial value of the A, and the B register can have the value 1100. So this is the B register. So here after applying the selective set operation, so here when there is a 1 in the B register, so here in this position the B register is having 1. The corresponding bit in the A register has to be changed to the 1. So here it can be changed to 1. Here in the next also one other occurrence of 1 is there in the B register, but the corresponding bit of the A is also 1. So there is no need to change. So after applying selective set operation, the result can be 1110 in the A register, which has to be given here. So which is exactly equivalent to the OR operation that can be applied between A and B. Next selective logic micro operation is selective complement. So here selective means when there is a 1 bit in the B register, then the corresponding bit in the A register can be complemented. So the operation complements bits in A where there are corresponding 1 in the B. Consider the same example. This is the value of A and this is the value of B before applying the selective complement. After applying the selective complement, here in the B, where is the occurrence of 1 has to be found. So here in this bit, the B value can be 1. The corresponding bit in the A can be complemented. So this 0 has to be changed to the 1. Next, the second occurrence of 1 in the B is at this position. So here the corresponding bit in the A is this. This can be complemented as 0. So the result of the A after application of selective complement is 0110, which can be a similar operation of exclusive OR operation. The next selective logic micro operation is selective clear operation. So here when there is a 1 in the B register, the selective, then the corresponding bit in the A register can be cleared. So clears to 0 the bits in A only where there are corresponding ones in B. So consider a example. A is initially having the bits 1010 and the B register can have the bits 1100. So after application of selective clear operation, first we have to find where there is a occurrence of 1 in the B register. So here at this position, the 1 has to be appeared. The corresponding bit in the A can be cleared 0. So it is already 0. So 0 has to be used here. And next, the second occurrence of the 1 in the B register is this position. The corresponding bit in the A register can be cleared. So here this can be 0. So after applying selective clear operation, the result can be 0010. So which is the selective clear operation. Next selective logic micro operation is the mask operation. So similar to the selective clear operation, the mask operation. So it is similar to selective clear operation except that the bits of A are cleared only where there are corresponding zeros in B. Okay. So selective clear operation it has to be similar to, but only the difference that the bits of A are cleared only where there are corresponding zeros in B. So here if you take the two registers as the example, A register, B register, A is having the value 1010, B is having the value 1100. So here we have to take the occurrence of the 1. So here it can be the 0 and here it is the 1. So here also the 1 can be the same bits can has to be transmitted as output. But here we have to look into the mask operation. It is different from selective clear operation. So here the 0 occurrence of the B can has to be identified. So here this is the first occurrence of the 0. So the corresponding bit in the A is also 0. So 0 can be used here. Next, second bit of B occurrence of the 0 is here and the corresponding bit can has to be changed to 0. So this is the difference between selective clear and mask operation. After applying the mask operation, the value in the A register is 1000. It can be similar to the AND operation of A and B. Next is insert operation. So inserts a new value into a group of bits. Okay. So here the insert operation inserts a new value into a group of bits. So here the steps for insertion operation are: step 1 is mask bits to be replaced. Next, are them with bits to be inserted. Two steps are there in the insert operation. Mask the bits to be replaced. Step 2 is are them with the bits to be inserted. So take an example. Consider an example. Insert 1001 in the left half of the word A. So we take the step 1 A. So A value can has to be given here 1001 in the left half of the step 1. So here A value can be considered here is 01101010 and the B value can be the 11100. So we have to apply the mask operation. So whenever the 0 is there in the B, the corresponding bit in the A can be cleared by applying the mask operation. Previously, how we did and considered an example. So after applying the mask operation, the A register value is this. In the second step, are them with the bits to be inserted. The bits to be inserted is 1001. So here A value can has to be taken here as A and B can be the inserted bit can be the left half of the word. So left of the half of the word 1001 and the B value the remaining bits can be 0. So insert operation and are them with the bits to be inserted. So we have to apply between A and B the OR operation. So the insert operation result can be 1001 1010. So this is the insert operation. So inserts a new value into the group of bits, but it involves the two steps. The first step is mask the bits to be replaced. The second step are them with the bits to be inserted. So this is the insert operation. Next is clear operation. Compare the bits in A and B and produces an all zero result of the if the two numbers are equal. So when A and B value are equal, then it has to produce the zeros. So here both are equal, so it can produce all zeros. So this operation is called the clear operation. So not only these 16 logic micro operation, additionally selective logic micro operations are there. The selective logic micro operations are selective set operation, selective complement operation, selective clear operation, mask operation, insert operation and clear operation. So after the logical micro operations, the next category of micro operations are the shift micro operations. These shift micro operations are especially important whenever the serial transfer of information is needed. Okay, so here during serial transfer of information, these shift micro operations can be implemented, and there are three types of shift micro operations: logical shift, circular shift, arithmetic shift. So these are the three categories of shift operation. In each category, again, two varieties of shifts operations can be implemented. They are left shift and right shift. So in the logical shift, logical left shift, logical right shift. In circular shift, circular left shift, circular right shift. And in the arithmetic shift, arithmetic left shift, arithmetic right shift. So totally 6 shift micro operations can be used. Now we will discuss each category. What is logical shift micro operation? So here the serial input transfer a bit to the rightmost position in case of left shift operation. The bits in the register has to be moved one bit either in left side or in right side in case of logical shift micro operation. So here first we have to discuss about the shift left. So here each bit has to be traversed towards the right position in case of this shift left operation. In case of shift right, the inverse traversal, so that the bits has to be moved to the leftmost position. So this is the logical shift micro operations. Now with an example, we can discuss what is the left logical shift. So here we have to consider one example bits. These are the bits in the register. So when you applied the logical left shift, the bits has to be moved one bit position rightward. So here this is the LSB bit. It can move to the next bit position here. Next bit can be moved, one bit can be moved to the next bit position. So like that the bits has to be traversed. So here what is the blank space that has to be there? This bit can be moved here so that the blank place that is here has to be filled with 0. And the last bit can be discarded. So this is called the left shift micro operation. Next is right shift micro operation. So here the bits has to be traversed here. So this is the example we have to consider. And whenever we applied shift right logical operation, the MSB bit has to be moved to the previous position. Like this, the bits can be moved. So here one is moved here, and an empty position is created here that can be filled with a 0. And the last bit that is there, that has to be discarded. So this type of shift operation is called shift right operation. Next is arithmetic left shift micro operation. Arithmetic left shift is similar to the logical left shift. So one position move each bit to the left by 1. So the vacant LSB position is filled with 0 and the MSB bit can be discarded. So it is similar to the logical left shift whatever we discussed. So the bits has to be moved, and here the vacant position can be filled with 0 and the MSB can be discarded. This type of operation can be called arithmetic left shift. Now the arithmetic right shift. The arithmetic right shift is have a slight variant from the logical right shift. How it can be means the MSB position has to be copied to the vacant position in case of right arithmetic shift. So the MSB can be filled with vacant position and can be moved to the next position. So like this, the right shift operation can be applied. So right arithmetic shift of one position moves each bit to the right by 1. Here all are moving right by 1. The least significant bit is discarded. So LSB can be discarded and the vacant MSB is filled with the value of previous. So here what is the previous value is there? That has to be filled with the vacant position. So this is called the right arithmetic shift. So what is the difference between logical shift and arithmetic shift? So here logical left shift and arithmetic left shift are the same. But in case of right shift only, the difference can be exist. So a right logical shift of one position moves each bit to the right by 1. The least significant bit is discarded and the vacant MSB is filled with 0 in case of logical shift. So here we are filling with 0 here. But in case of right arithmetic shift, now one position moves to each bit to the right by 1 and LSB can be discarded and the vacant MSB can be filled with value of previous. So here the previous can has to be filled here with the vacant position. So this is the difference between logical right shift and arithmetic right shift. What is the purpose of this arithmetic shift operation? So with the help of arithmetic left shift, multiplication can be performed. The result of a left shift operation is a multiplication by 2 power n, where n is the number of shifted bit positions. So consider an example, a decimal number 2 and the 2 has to be represented in 4-bit binary number as this. So the decimal 2 value can be represented with a 4-bit binary 0010. After applying on this 0010, the left shift operation, we can get the value of 0100, which is equivalent to the decimal value 4. So here by using the left shift, the multiplication of by 2 power n value has to be represented. So we taken 2 and after left shifting we can get the 4. If the 4 value if we left shift, we can get the 8 value. So like that the left shift can be used for multiplication. Next, division by right shift. Arithmetic right shift has to be used division by 2 power n, where n is the number of shifted bit positions. So consider an example that a binary decimal number 117 is determined with the binary values 0, 111, 101. So which is equivalent to the decimal value 117. So after performing arithmetic right shift by 1 bit, we can get the binary number 58. So here the value after applying the arithmetic right shift 00, 00, 111, which is equivalent to 58. So arithmetic right shift has to be implemented so that the division operation can be performed by 2 power n, where n is the number of shifted bit positions. So this is the purpose of arithmetic shift operations. Next, a variety of shift is the circular shift. The circular shift circulates the bit in the sequence of register around the both ends without any loss of information. So that we can call it as circular shift. So here, whenever you performed the left shift operation, so here the MSB can be discarded in previous cases. But in this circular shift case, it cannot be discarded and it has to move to this end where vacant position is available in the LSB has to be filled with the discarded MSB bit. So that's why this operation is called circular shift operation. Similar way, circular right shift. So here the discarded LSB can has to be filled with vacant position that is available at the MSB. That operation is called right circular shift. So shift operation is useful for the serial communication of information can be needed. So three varieties of shift operations are there. Logical shift or the normal shift operation, arithmetic shift operation and circular shift operation. In each shift operation, again two varieties are there. They are the left shift operation and right shift operation. So 6 shift micro operations can be applied. What are the assembly language mnemonics can be used for these 6 micro shift operations? So here SHL, that is the shift left. Okay, so shift left register content of R and can be moved to the R. This is the RTL notations of the shift micro operations. Next is SHR, shift right the register content of R and can be moved to the R. So this is the normal shift operation, shift left and shift right, and can be using the mnemonic SHL, SHR. Next is CIL, circular left shift. Circular left shift, the register content R. Next is SIR, circular right shift, the register content R. After that, the arithmetic shift operations. The arithmetic shift operations can be represented ASHL, arithmetic shift left. Next, ASHR, arithmetic shift right. So these are the 6 shift micro operations. These two pertaining to the logical shift operation. These two are the circular shift operations. And these two are the arithmetic shift operation. In 3 categories, the left shift and the right shift, and CIL and CIR for representing left shift and right shift respectively, and ASHL and ASHR is used to represent the left arithmetic shift left and arithmetic shift right respectively. So these are the assembly language mnemonics that can be used and the RTL notations that can be represented for the shift operations. Now we have to discuss about what is the hardware requirement circuitry for these shift operations. So the register has to be taken with 4-bit input A0, A1, A2 and A3. So this is the input. And the output from the circuit is H0, H1, H2 and H3. So this has to be, the output can be derived from the multiplexers. So the right shift operation and left shift operation can be represented with this. And this is the 2 operations has to be selected. So one control line can be required, that is this selective line 1. When this S selective line is 0, the right shift operation can be performed. When S value is 1, the left shift operations can be performed. So here the selection of input can be taken care by this multiplexer. So this is the circuitry required to perform the shift micro operations. So this is the truth table of the shift micro operations. When S is equal to 0, the right shift operation IR right shift operation can be performed. When S is equal to 1, the left shift operation IL has to be performed. So this is the truth table of the shift micro circuit. So here in this video we discussed what are the logical operations. So here a list of 16 logical operations, how they can be performed along with their truth tables are discussed, and they can be represented in RTL, and what are the hardware implementation required for logic micro operations are discussed. Next, Not only these 16 logic micro operation, additionally selective logic operations, how they can be implemented with examples we discussed. Next, we move to the shift micro operations. Three varieties of shift: logical shift and circular shift, arithmetic shift operations, along with two varieties of left shift and right shift we discussed, and how in RTL they can be represented. What are the respective assembly language mnemonics used for the shift micro operations, and how they can be performed with the respective hardware circuitry we discussed. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.